Welcome back, everyone. Today, we're diving into an absolutely crucial pillar of professional software engineering, and that is version management. Look, if you've ever worked on a team project and accidentally deleted a teammate's hard work, well, you already know exactly why we need this. In modern software engineering, we're building incredibly complex systems, and managing how those systems change over time is just essential. So this explainer is going to give you the formal technical understanding of how we prevent total chaos when multiple developers are modifying the exact same software system at the exact same time. Let's get into it.
Here is our roadmap for today's lecture. First, the overwrite problem. Second, core vocabulary. Third, centralized systems. Fourth, distributed systems. Fifth, open source workflows. And finally, storage and our lecture summary.
All right, part 1, the overwrite problem.
Let's start with the fundamental reason version management even exists. Picture this highly relatable nightmare scenario. We've got two developers, Alice and Bob. Now, Alice is busy making changes to a system, and her task involves editing components A, B, and C. At the exact same time, Bob is working on his own completely separate task that requires editing components X, Y, and, you guessed it, component C. So both Alice and Bob are modifying component C simultaneously. If we don't have a robust system in place to manage this concurrent teamwork, it basically becomes a race. Whoever hits save last is going to completely overwrite the other person's code. Bob's save could literally destroy hours of Alice's hard work, leading to massive data loss and, frankly, a lot of team frustration. So the core problem version management solves is preventing this interference. We want to ensure that developers can work completely independently without destroying each other's contributions.
Moving on to part 2, core vocabulary.
Before we can actually solve this overwrite mess, we really need to get our terminology straight. Whenever a technical term appears in software engineering, it's vital to define it clearly first. So here's a glossary of formal terms that you absolutely must recognize. Let's highlight the most important ones. A configuration item is basically anything associated with a project that has been placed under configuration control. This could be a design document, test data, or a source code file. A version is simply a specific instance of that configuration item that differs in some way from other instances. And a repository, well, that's the shared database that stores all these versions of our software components, along with all the meta information about the changes made to them.
Now, here is a distinction you absolutely need to nail down for your exams: the difference between a code line and a baseline. Let's break it down. A code line is a sequence of versions of one specific component over time. For example, version A1.1 becomes A1.2, and then it becomes A1.3. It tracks the history of a single piece of the overall system. On the flip side, a baseline is like a snapshot. It's a specific collection of component versions that, together, make up a complete working system at a single point in time. So in baseline V1, we might be using version A1.1 of a component, but by the time we hit baseline V2, we've upgraded that specific component to version A1.3. A really common mistake students make on exams is assuming these two terms are interchangeable. They are not. Just remember, code lines track individual component history, whereas baselines define a whole system snapshot.
Okay, part 3, centralized systems.
So, having established that vocabulary, let's look at the historical solution to Alice and Bob's problem: centralized version control systems. A classic example would be Subversion, or SVN. In a centralized system, there is exactly one master repository sitting on a central server somewhere. Alice checks out a file she needs into her private workspace, makes her changes, and checks them back in, creating, say, version C1.1. But what happens to Bob? Well, Bob originally checked out the exact same version, C1.0. When he finishes his work and tries to check it back into the master repository, the system stops him dead in his tracks. Because Alice has already updated component C, the system forces Bob to merge his changes with hers before it accepts the new version, C1.2. This ensures mathematically that no data is lost.
Let's break that down into a strict step-by-step sequence. First, developers check out specific files from the single master repository. Second, they edit those files locally in their own private workspace. Third, they attempt to check those files back in. If the files have changed on the master in the meantime, they are forced to resolve the conflict right then and there. To recap, centralized systems, developers rely entirely on one single master repository acting as the absolute source of truth, and the system actively blocks conflicting check-ins.
Which brings us to part 4, distributed systems, and specifically Git.
Let's see how this builds into the modern evolution of these tools.
In a distributed version control system like Git, we handle things completely differently. We don't just check out a few isolated files. Instead, every single developer downloads a complete clone of the entire project repository straight onto their local machine. So Alice has the whole history. Bob has the whole history. They're no longer constantly tied to a central server just to check the history of a file or commit a new version. They make commits to their own local repositories first and only share them with the rest of the team later on.
Now listen up, because this is a highly testable concept. Why did distributed systems become the absolute industry standard? There are 3 primary advantages you need to know. First, it acts as an incredibly robust backup mechanism. If the main master server suddenly catches fire, it actually doesn't matter. Every developer's laptop contains a full, complete backup of the entire project history. Second, offline working. You can sit on a long-haul flight with absolutely zero internet access and still commit changes, view file history, and create local branches. And third, project support. Because you have cloned the entire repository, you can compile and test the entire software system locally before you ever push your code to the rest of the team.
Part 5, Open Source Workflows.
Because Git gives everyone their own full, independent copy of the repository, it fundamentally changed how we build software. It literally paved the way for massive open source development. Think about it. You don't need to give hundreds of random strangers write access to your master codebase anymore. This introduces the Integration Manager workflow. Here's how it works. Alice and Bob make changes in their private repositories, and then they push those changes up to their own personal public repositories. Then we have Charlie. Charlie acts as the integration manager. Think of someone like Linus Torvalds managing Linux. Charlie reviews Alice and Bob's public code. If he likes it and it passes his checks, he pulls their changes into his private repository, tests it out, and then he is the only one who pushes it to the definitive master project repository. When you have all these different developers working completely independently, they create what we call branches. Now, to define that, branching is the creation of a new, independent code line from an existing version. It lets you experiment, build new features, or fix bugs without breaking the main system. But eventually, we need to bring all those separate experiments back together. This is called merging, the process of combining those separate code lines back into one. Often, the system does this automatically, but sometimes if Alice and Bob have changed the exact same lines of code, they'll have to jump in and manually resolve those incompatible code clashes. So just to quickly recap, distributed systems empower independent branching, which ultimately requires an integration manager or a merging system to safely bring that code back together.
Finally, Part 6, Storage and our lecture summary.
Okay, practical computer science question time. If we are meticulously tracking every single change and every developer is cloning the entire history of the project to their laptop, how do we not just instantly run out of disk space? Well, older centralized systems solve this by storing what are called deltas. A delta is simply the mathematical difference between two files. So instead of saving a brand new copy of a 10,000-line file when you only changed one word, the system just saves that one changed line. To rebuild an old version, the system has to apply a long chain of these deltas. But as you can imagine, applying thousands of deltas is really slow. Git takes a completely different approach. Because disk storage is much cheaper these days, Git relies heavily on standard file compression. It stores whole files but compresses them heavily, and it frequently combines multiple smaller files into single, indexed pack files. This massively speeds up file retrieval. It's a calculated trade-off that intentionally prioritizes speed over saving every last byte of space.
Let's do a quick recap to ensure you can prioritize your studying effectively for the exams. Remember the core goal: preventing developers like Alice and Bob from overwriting each other's work. You absolutely must know the definitions. Baselines are whole system snapshots, while code lines track the historical sequence of a single component. Be able to contrast centralized architectures, which rely on a single master, with distributed architectures like Git, where everyone clones the full repository. Memorize those 3 advantages of Git: backup, offline working, and local project support. And finally, understand that Git uses compression and pack files for incredible speed, rather than relying solely on slow chains of deltas.
Before we wrap up this explainer and transition to our next topic on system building, I want to leave you with a final thought to ponder. We now have a system that permanently records every single line of code ever written, including all of our bugs, our errors, and our really bad ideas. If version control meticulously tracks every change we ever make, how will future automated systems, or even AI, learn from the billions of mistakes we've permanently preserved in our code lines? Something to think about. Thank you so much for joining me for this lecture, and I will see you in the next one.